My name is Matt Emery. As mentioned, I work at a company called Embodied. We focus on educational assessment, and I'll talk actually a little bit about like what we do further into this talk, because it actually does touch on a little bit of what we do. But I'm a senior data scientist there, been there for a bit, and this has nothing to do with my job. I just really thought this was a cool problem. I think that we're kind of attacking a very foundational idea in the field from a little bit of a new direction. So this is the Abstraction and Reasoning Challenge. It was called Kaggle's Toughest Challenge. It was also called Kaggle's Most Important Challenge. So there's a lot of weight on this challenge, and I will barely be talking about the challenge. Sorry. All right. So let's start. I have two puzzles for you. All right. Here's the first puzzle. Take a look at the left here. You'll have pairs of boxes here, where the first column is matched with the second column, right? And you have to figure out what the pattern is. And if anyone can guess what the solution for this test input is that's in the middle here, please shout it out or type it out.
Two red blocks in the middle?
Two red blocks, yeah, like down?
Yeah.
Yes. Yes, correct, right? So that's the first puzzle. Here's the second puzzle. Why are machines so bad at this, right? It seems like something, when we look at it, like I didn't have to train you to do that. You were just able to immediately guess it. I'm guessing most of the people like got it like quite fast. Machines, they're just very bad at this, and it's kind of confusing why. A lot of things that we think are hard, machines find easy. A lot of things that we find easy, machines seems hard. So, talk outline, what is the goal of this competition, right? Then in bold, what is intelligence? Very scary question, and going to be the majority of this talk. Then we're actually going to get to the abstraction and reasoning corpus, and then some attempts to solve this problem. All right, so what is the goal of the abstraction and reasoning corpus? Just to the right here, we have Francois Chollet, who's been mentioned multiple times. He is the author of the Keras deep learning library, which is kind of like the library that you want to start with. I know when I started doing deep learning, I started with Keras. I still think it's a great library. It's probably one of the best designed ones that we've seen. In addition to designing a library that so many machine learning researchers use, he's also a pretty prolific researcher. He works at Google and is like overall a very smart guy. He also has a Twitter account where you can see him complaining about things. So here is his proposal for the abstraction and reasoning corpus, which he essentially made. The abstraction and reasoning corpus provides a benchmark to measure AI skill acquisition on unknown tasks with the constraint that only a handful of demonstrations are shown to learn a complex task. It provides a glimpse of a future where AI could quickly solve problems on its own. Now, generally, when we're talking about what artificial general intelligence is, which is the sort of Hollywood idea of an artificial intelligence that is doing usually evil things, because it's pretty boring if artificial general intelligence just solves everyone's problems, but your HALs, etc. People are talking about artificial general intelligence, and we're not there yet, right? All right. So think about that previous puzzle that I gave you. What percentage do you think of problems like that do you think a machine should be able to solve, right? So actually, let's not even talk about like the average machine. Let's talk about the best, like the best solution that someone came up with for an AI that can solve it without actually having to see, without having the answer pre-programmed into it. Just guess. Actually, I would love for you people to just write in the chat. But Matt K, if you could just tell me a few guesses, that'd be great. Also,
Okay.
Don't look ahead of time if you know.
I said 60%, 1%, 14%, 11%, 50%, 3, 25, 30, 30, 1, 25.
It's a good spread. I like that spread.
But I think you've set us up for it being low.
Yeah,
I think you've also led people on by saying AI, because the techniques employed by people in this competition were not machine learning.
Yes. Yeah, we will definitely get into that. I love the first person, their answer for like, how did you solve it? But we'll get to it in the future. But yes, so it's probably a good idea to guess a little bit low. Okay, what is the goal of AI research? Let's ask Marvin Minsky. He's one of the founders of AI. This was way back in, I believe, the 50s. AI is the science of making machines capable of performing tasks that would require intelligence if done by humans. Okay, great. Where does that get us? Well, not very far, because now we have to define what human intelligence is, right? So a lot of people find this definition of AI to be a little bit iffy and not all there, right? Like it's kind of like a nice sort of summation of what we want, but it actually doesn't quite scratch that itch, you know? So we're gonna have to go a little bit deeper. So weaknesses of our current AI approach: we have been fantastically successful in a lot of different things, and especially with like narrow kind of focuses. Object recognition has been great, text to speech, all sorts of problems have been revolutionized by deep learning, but still it seems like we have a long way to go. So the current algorithms that we have are narrow, right? So they can't answer multiple tasks. Or if they do, they tend to not be as strong as individual type machine learning models. The famous AI competitions like the Turing test, they don't really get us to where we need to be, because they rely on human judges, which just isn't very scalable and also is quite subjective. As an example, so the actual instrumentation of the Turing test is called the Loebner Prize, and it's just you have a person and they're typing at a chatbot, and you have to, well, they're typing at someone and they have to guess whether or not it is a chatbot or a real person. And apparently the highest scoring chatbot currently is a sarcastic Russian teenager chatbot that whenever you ask it a question that it doesn't know, it just goes like, why would I answer that? This is boring. So that probably isn't what we want in AI, is just someone saying like, I don't know, you tell me. But there is like a serious problem with this, which is the lack of agreement on what intelligence is, and like an actual way of defining it does bias towards just these narrow types of tasks, right? So it's really easy. Well, it's not really easy, but when it comes to measuring progress, it's a lot easier to measure progress in, say, the number of images correctly recognized in ImageNet than it is to measure what intelligence is, right? Or like, what is the IQ of X bot, right? It just doesn't seem to make sense. All right, so just updating a little bit. Marvin Minsky, 1950s. Legg and Hutter are still around, and they have done a lot of work on this. And they have what I think is a better kind of definition of intelligence, which is intelligence measures an agent's ability to achieve goals in a wide range of environments. Again, quite broad, but we want this definition to be really broad. Intelligence is a very broad concept, right? You can break that down into kind of two parts here. The first is achieving goals, which is how we tend to benchmark things right now. Again, object recognition or semantic segmentation, lots of great data sets for that. What Cholet is interested in is the wide range of environments part, and he has a few philosophical reasons for caring about this. One is, we have a ton of research on that first part. The second part seems to be underserved. All right, measuring the right thing. His general argument is the real world is chaotic, right? And in a chaotic system, it's better to care about adaptability, because that will get you back into a little kind of stable island where you can actually make meaningful decisions. Whereas if the underlying distribution of your data set is constantly changing, you really aren't going to get much from the way that models currently work. He also further argues, and I think this is a little bit debatable, that Deep Blue and OpenAI 5, which was the Dota bot, and AlphaZero, which is one of the Go bots that Google made, they actually didn't get us that much closer to AGI. They were extremely good at solving some tasks, but as we've seen, there hasn't been a ton of follow-on research about, okay, well, now let's apply the OpenAI 5 Dota bot to something important like the traveling salesman problem, or just a general question answering machine. That's because it is still quite narrow, right? He also makes what I think is kind of like a nice or maybe like a flattering kind of statement here. And he says that often these challenges measure the intelligence of the machine learning engineer, not the system itself. There's a lot of art to building a really great machine learning system. And a lot of that is actually encoding what he calls the priors of the system into whatever learning system or whatever learning algorithm is being used, right? So when we talk about image recognition, we always talk about convolutional neural networks. And there is some evidence that convolutional neural networks kind of act like the way that Gabor filters, which are how our eyes supposedly detect edges and stuff like that. On the side, I have a poster for AlphaGo, which is a documentary. I tried to see if it was on Netflix. It looks like it isn't anymore. But it is a really nice documentary just watching the team involved with AlphaGo, which is one of these reinforcement learning algorithms. Just watching their kind of struggles as they try to beat the world grandmaster at Go. At this point, any questions? Anything in the chat?
I second it was a good movie.
Okay, great. Yep.
Not quite a question that might be answered in one sentence, but Matt can help us understand. Sometimes I think of human intelligence as something that has helped us survive for several thousand years, right? So it's something that's not just the brain, but it's also kind of inherited through evolution.
Yeah.
And so the whole idea of trying to build something together on a computer, which really doesn't have the same kind of infrastructure as a brain, I'm not sure how that's going to pan out. The example I'm always using is the termite mounds. We have termite mounds. They are not inherently smart, but they build queen chambers, nurseries, and they farm, right? Mm-hmm. So there's some kind of an emergence that happens with the complexity of the human or the cellular structure itself. So I'm not sure if transistors can mimic that. This is just me being the pessimist.
No, yes, this is a totally valid philosophical position. This kind of comes into the idea, and it's not in my slides, but the idea of embodied cognition. There are some RL researchers, or I guess you would say AI researchers, but specifically in RL, that say if you want an AI to think like a human does, you should give it a robot body that acts like a human, right? One of the things I was thinking about as I was kind of compiling these slides, so just to kind of go ahead here, there are priors given for counting up to 10. I think that, not being an expert in this, I think the reason why we have the sort of ingrained ability to think about small groups of numbers up to 10 is because we have 10 fingers, right? So it's really easy to point at a thing and also stick your finger up. So there's one of it, or you go there's two of it, and then you can go there's 10 of these, right? But yeah, that's a valid position. When I think about intelligence, termite mounds I could consider intelligent. I also think things like markets can be intelligent or not intelligent, depending on what the market is. And that there's all sorts of organizational intelligences as well that don't actually have consciousness. The reason why I take that position is because I really don't like thinking about consciousness as it deals with intelligence, especially when what I really want is I want Siri or one of those kind of chatbots to actually understand what I want instead of what it has just garbled, right? So I don't really care if Siri is conscious. What I really want is I don't know, for it to actually get the kitchen timer correct or whatever.
Yep, I agree with that completely.
Yeah. All right. Okay, I'm going to keep on going, but stop me at any time. So current trends in AGI evaluation, lots of reinforcement learning. what tends to happen is that most RL tests are not robust, right? And there is no measurement of robustness. By robustness, we mean if we change the kind of underlying conditions of the game or the environment, can the machine adapt to it? Usually not. Also, reinforcement learning algorithms have a really nice property that I am very envious of as someone who does not do RL, in that you can essentially sample arbitrary amounts of data. So a lot of these algorithms, like AlphaGo, was trained on like 10,000 years worth of Go games. And I don't even know how much the OpenAI Dota 2 bot was trained on, but it was, I think, on the order of another 10,000 years of just playing a video game over and over again. And even with all of that, it breaks in certain places that we really don't want it to break. So for those of you who don't know, I don't know a ton about Dota 2, so please forgive me. But it is kind of like a strategy game where each side controls 5 heroes. Those heroes have to work together to destroy each other's bases, et cetera, et cetera. There's a lot of long-term planning involved. And OpenAI, a rather famous kind of research, I guess, fund, institute, I'm not sure what to call them, they created like a sort of network of bots that beat some of the best players in the game, and then they opened it up to just the public. And pretty soon, the public started realizing, oh, there are certain things that we can abuse about this bot. So someone discovered, and this is what this tweet is trying to say, and honestly, it took someone like 15 minutes to explain like why this is funny, and I still don't think it's funny. But essentially, you can abuse the fog of war system inside of Dota 2 to cause the OpenAI bot to teleport to a cliff that it can't get off of. So it is like out of the game until it like kills itself or like somehow can get off of it. So I guess teleporting back. So that's something that you would hope that humans don't do. Obviously, this Arteezy guy has done that in the past, and people still make fun of him for it. So I guess it's kind of human. But that is essentially what the tweet is trying to show. All right, just want to briefly talk about the AI effect, which is every time somebody figured out how to make a computer do something, there was a chorus of critics to say that's not thinking, right? And I think I am probably also going to be part of this chorus of critics for some of the solutions that we see later. But there is sort of a magical idea that like AI is whatever the next thing is, and at what point will we be satisfied with artificial intelligence actually being artificial intelligence? Because I remember growing up in the idea of even like an AI that could pick out the different objects inside of an image was pretty crazy, very like cutting edge stuff. But now we just say, oh yeah, like it's obvious that it can do that. So with that in mind, let's dig a little bit deeper on what we actually want in a benchmark. So we know we don't want just like a single skill, but what else do we want? We want things to be reproducible, right? So if we give this AI a test once and then we slightly perturb the settings or change the random state, we want the AI to do roughly as well as it did last time. We want it to be fair, and this is fair to the machine and also fair to the humans. So this is a really important part of Francois Chollet's overall philosophy. Is he essentially says, look, the best example we have for intelligence is humans. We should just be trying to reverse engineer humans instead of trying to come up with a totally new idea of what intelligence is. This is a fairly controversial idea. But when he's talking about fairness here, he is actually mostly talking about, is this fair to the machines? Like, are there things that we know that the machine can't know? And are we fair to the humans? Are there certain things like, say, speed that the machines have that we just don't have? Scalability, obviously. So again, with the Turing test example, just getting a bunch of people in the room, typing with a chatbot, like that just isn't very scalable if we want to actually get anywhere. And then flexibility in generalization. So what we really care about is, can this solve like a wide range of problems, not necessarily can it solve each individual problem really, really well. Any questions at this point? So take a sip.
I have a question.
Mm-hmm.
So like by fairness, it doesn't mean like not introducing bias into things. It's kind of not along those lines.
Yeah. We'll get to like a more thorough definition of what fairness is.
Okay. It's an interesting word choice that I would have assumed meant something else.
Yeah, I remember when I read it, I was like, okay.
Okay.
He is, in some ways, trying to model his test, and we'll see a little bit coming down here. He's trying to model his test over kind of the gold standards for IQ testing, right? Which obviously has their own problems.
Right.
But one of the stated goals of IQ testing is to be fair, right?
Okay.
So
okay. Cool.
There's a little bit of that going there as well. Any other questions? All right, let's keep on going. All right, so before I can actually get into like what is he talking about, he makes some really what I think are astute observations about the nature of generalization. The first thing he does is he makes a distinction between two different types of generalization. The first one is system-centric generalization. So I think maybe not all the ML engineers here, but many of them have encountered cases where you have what you know to be an unbalanced data set, and you try to compensate for it in some way, right? You have like a minority class, and then you might oversample, or you might undersample the majority class in order to try to get the algorithm to correctly predict on what the actual distribution of cases may be, right? So that's something that you as the developer are aware of, right? Or that's like a known unknown, right? So we don't actually know exactly what the true distribution of these cases are, but we know the general direction of it. And then he wants to contrast that with something called developer-aware generalization. So what are the things that the developer just cannot know about that just comes out of the blue like a lightning bolt and then changes everything? And there are a lot of different failure modes in this, and a lot of them can be like very devastating. And we've seen a lot of weaknesses here with that. And here is an example.
I have a question.
Yeah.
So I used to think generalization is like distribution specific, or is that still the case, or it is arbitrary to any distribution?
Yeah. So just before I answer, I want to make it clear that this particular crash does not have anyone dying. The person who crashed here did not die. Just in case you're getting it looped over and over again and are concerned. Yes. Normally, this is distribution. Like the way that we typically think about generalization is distribution awareness, right? And what Cholet is saying is distribution awareness is not enough. We need to have algorithms that are capable of responding to changes in distribution that would not be possible for the developer to be aware of ahead of time. So, like, what would be really great if you had, say, a forecasting type algorithm, right? Is there's a black swan event. Say there's some sort of global pandemic or something like that, and then someone like me has to do this talk over Zoom instead of in person. The algorithm should not completely fail because of this sort of black swan event. It should be able to respond in some way, and that's kind of the hope, right? Now you can try to pre-program it for some things, but if it's a sufficiently complicated algorithm, you can encode all of these different black swan type events. Does that make sense?
Yes, it does.
Okay, cool. Right. So this is an example of something like of developer-aware generalization. So those of you who drive, if you saw an overturned truck on the road, you would know, oh, that means I should probably avoid the overturned truck, right? This is a Tesla autopilot. This was a crash that happened in Taiwan. And as I said, the person who was not driving, in this case, it was autopilot, walked away from it. There have been other cases where people have not, right? But this is like very out of distribution. How many times in your life have you seen a truck overturned with this specific kind of angle? Probably not very often. Like I think I may have seen a single overturned truck in my entire life going down the highway. But regardless, we would all know, don't crash into the truck. Like, why does autopilot not know that? And this is the kind of getting to the idea of developer-aware generalization. It just hasn't generalized beyond all the things that you train it on. Does that make sense? Good. Right.
Matt, maybe the AI there is Marvin or Mervin.
What?
Oh, Hitchhiker's Guide to Galaxy, the most interest AI.
Yeah.
So
yeah, it's not worth living, but it should also follow Asimov's rules. So this is boo. We need more of our sci-fi. Okay, so we have these two types of generalization. We also want to talk about the spectrum of generalization, right? So you can kind of imagine like two lines here, and then Cholet says, well, our goal is extreme generalization. You should be able to ask your AI essentially anything. It should be able to solve that task with a reasonable, like it should reasonably solve like basically all tasks that a human could do, right? So kind of going back to Marvin Minsky a little bit. But at the very, we're going to say like the very left side of this, you have the absence of generalization. This is like a classical algorithm, like a sorting algorithm, where there can be no uncertainty involved. You just, if it's all integers, it will sort integers. If there's also a string there, you don't know what to do. It's just going to, fail. Then you have local generalization, and we're pretty good at this, right? So this is like the classic, here's like a KNN clustering algorithm. And you say, okay, well, all the other points in this 2D plane are red, or all the nearby points are red. So this point should also be red, whatever that is, right? Broad generalization is, and I think this is actually a really nice kind of summation of like what we want out of AI. Is that the idea of Wozniak's coffee cup challenge. And this came from a 3-minute interview with Steve Wozniak, who was one of the co-founders of Apple, and they asked, how do you feel about artificial intelligence? And he says, I'm not going to feel worried about it until I can talk to a robot and say, make me a cup of coffee, and that robot can find the coffee room, find a mug, make me a cup of coffee, and then come back and give me the coffee without burning me. So that would be an idea of like broad generalization, right? Is across many different scenarios, you could make a cup of coffee, right? So trivial for us, very difficult for machines. Okay, just going back to Marvin Minsky here, would require intelligence if done by humans. You know what? We should actually look at how we measure intelligence in humans. And that's done through a field called psychrometrics. This is actually part of what I do like for work, where there is this concept of G, right? This extreme generalization type. Sometimes this may be measured through like IQ. My company is personally interested in the second layer, which is the broad cognitive abilities. So you can have I tend to actually use the athleticism analogy a little bit more because I find that a little bit easier to grasp. So if you see an elite level Olympic athlete, let's say that they're an amazing shot putter, right? They are not only really good at shot put, they're also probably really good at a lot of different things, right? So they may also be like really good baseball pitchers, or I don't know. They're probably not, if it's a shot putter, this is not a great example, not great at track and field, but like in general, if someone is very athletic, they tend to be really good at all sports, right? Underneath that, there are different, abilities. So that's your strength. That's your, top speed when you're running, your VO2 max, right? Your ability to just expand your lungs quite a bit, your ability to regulate heart rate, etc. And oftentimes these abilities may be hard to measure directly. So what you need to do instead is to give a bunch of tests for these abilities through just individual tasks, right? So I may ask you to run like the 100-meter dash and the 400-meter dash and do hurdles, and then I don't know what else is in the track and field meet. But overall, if you were really good at all of them, I'm going to guess you have a high athleticism. And the same is true for intelligence. If you're really good at math problems, you're really good at reading paragraphs of stuff, you're really good at logic, you're probably actually going to be like pretty smart overall, and that's what is generally found.
Ask one question there.
Yes.
Is that implying that is the word generalization implying that the intelligent person can generalize, say, from task 1 and learn to do task 2, or is it implying something different?
Yeah. So the way that you should kind of think about these arrows is I would actually probably reverse them and then think about each individual task gives you evidence for different cognitive abilities, and then the overall like level of each of those cognitive abilities. Like, let's say that you're a very good mathematical thinker, and then you're also a really good like logician, right? Those are very related, but it's been on my mind recently. That probably also adds evidence to your general intelligence as well. Your G factor, which is
okay. So it's more like generalized than generalization. It's not implying generalization as a measure of intelligence. Okay.
Yes, but then like if you think about what we want out of an AI system, right? We want something with a very high G because then it can solve all of these tasks, right? So we're looking for evidence in the one direction, but then we want to produce something that like does really well on the tasks because that's like ultimately what we care about, right?
Yeah.
Already pretty much talked about it, but one important kind of caveat here is talking about this athleticism analogy. You wouldn't measure someone's athletic ability at the bottom of the ocean or on Mars, right? We have certain assumptions that we make, right? And at the same time, we have certain assumptions about like what is intelligence, and it, surprise, surprise, it biases towards human intelligence. And there's a really nice passage in the paper that Chalet wrote about this competition where he asked if the octopus's ability to camouflage is a sign of intelligence or not. And I had never really thought about it. I think it probably is, right? But we don't. That's not on any IQ test. Is how good are you at camouflaging amongst a bunch of sea anemones? The same can be said with how we perceive things. So we're really good at 2D and 3D problems, but as soon as we get into 4D, and especially if we get into 5D, we're utterly hopeless at solving these problems, right? Without some serious backing of like linear algebra or something like that. So if we want to be fair to the humans on this side, we should probably look at problems that are in 2D or 3D. All right, so just a few more lessons from Psychometrics, and I swear we are almost there. We are almost at what this competition is about. We want to measure these abilities, not the skills, right? Especially because a lot of these skills can be ingrained and trained. We want to use a battery of tests, right? Not just one. We want to set reliability and validity standards. So reliability means a lot of different things, and so does validity inside of Psychometrics. But as like a layman, I can tell you that reliability tends to mean if I test you today on something and then I test you, 2 days after, you hope that you get around the same score each time, right? That would be a reliable test. And validity is this idea of, okay, so you scored really high on, let's say, ARC, right? You want to be able to apply that to like the wider world, right? So just kind of going back to this, if we say, oh, you're so strong, you got a great bench press, you got a great squat, et cetera, but you cannot lift groceries to save your life, there's probably an issue with the way that we're measuring strength, right? So we want to remove the need for non-universal knowledge, right? So we don't want to add in, ideas about like what a cat is, what a dog is, let's see, what else we would, basically everything, right? So any like NLP and image recognition is really not a part of this test, right? So the hope is that once we actually get all the image recognition and all the NLP done, we can reduce it down to something that an ARC solver could theoretically work with. And then, we want to focus on skill acquisition efficiency. So how fast does it take does it take the machine to learn something? Okay, again, almost there. Human priors, as was it Sam who mentioned this? There are things that we just have naturally evolved into us, right? We are not blank slates. At the same time, like there is not like a limited I guess I don't want to say like biology is not destiny here, but there are certain things that just everyone has, right? The idea of object permanence. And if you can see my screen here, you see that I have a pen up here, right? And I drop my hand down and bring it up. You automatically know that I'm talking about the same pen, right? So why is it that we have that and machines don't, right? So that's like one of the priors that Cholet kind of claims that we all have. He also talks about reflexes as actually a pretty good example of what priors are, but not really relevant to this, right? Another thing that he talks about is meta-learning priors. So we are extremely good at learning things. That's probably what separates us from all the other animals, is our ability to learn things and quickly communicate, oh yeah, this is how you do this. We have been fantastically successful on the evolutionary scale by being able to learn things. So we would love to put in those priors, like how is it that we were so good at learning things into the machine, but we actually just don't know what they are yet. And Cholet's kind of goal here is to reverse engineer those meta-learning priors. And then lastly are these high-level knowledge priors. So I talked about object permanence, but there are a whole bunch of others. We want all of those to be enumerated. I'm just going to go through here. And here's just a big list of them. And now we're going to go back to playing some games, some puzzles, right? So very quickly, object recognition, cohesion. So, when I show you an object that is a pen, right, you know that this little metal part is also part of the pen, even though it's a different color. Persistence, contact, you know that when I have two pens together, right, and they hit each other, one is not going to phase into another unless there's like a very rare quantum event. So those are all things that we just know, right? And we also are really good at looking at like scenes. Like, for example, animation. We're really good at projecting emotions onto cartoons. And that's like something that is ingrained in us. We can look at symbols and we can look at, from one scene to another, what's going on. Some examples are like when a block kind of swerves out of the way of another block, we say, oh, like that one block, avoided the other block. And then also you can just put two blocks and have them kind of walk across the screen, and you say, oh, block A is being chased by block B, right? Natural numbers, basic arithmetic, and then a bunch of things about symmetry. We're really good at checking out symmetry. And there's a lot of like really interesting ideas about like why is that, but I don't have time to get into it. How much time do I have left, by the way?
Sorry, I lost my clock too.
7:33 right now.
7:30.
Okay, yeah, we're good. Yeah. Okay. So take a look at this. Does anyone want to take a crack at what the answer to this would be? Or write it down in the chat and then get Alexi or Matt to answer for you. Going once? Going twice?
Can I take a stab?
Yes, please.
So the red squares, it kind of extends upwards,
Yep.
and if it doesn't run into a gray block, it'll reach the top as is. But if it does run into it, I think it shifts to the right and then keeps on going.
Exactly correct. That's the solution, right? So what does that tell us? It tells us a little bit about the idea of contact, right? It doesn't phase or go directly over the gray block. And it also has this kind of concept of goal directedness, right? So it seems like the red block wants to get to the top, right? Even though, it's not doing anything of the sort. It's the red block, right? Okay, here's another one. And want to take a guess? And by the way, none of these are like tricks, right? Like they're all exactly as hard as suggested. And they should be relatively easy for humans to do.
So the yellow block wants to eat the turquoise block.
Yeah.
In the terms that you're using.
Yeah, sure. Yeah. So we're talking a little bit about distance. It goes up until this light blue block, right? Also, this sort of in-out relationship is being expressed here as well, right? Like we would say that the yellow is enclosed by the purple or the pink magenta. So it looks like this. Right? Makes sense? Okay, now I have a hard one for people. And I'm going to let people kind of look at this a little bit. It did take me a little bit of time. And then those of you who have like tried to program before, try to imagine how you would write the program that could do this. And if anyone wants to take a stab, please do. But I might just give it 15 seconds and then give you the answer, because I found this one pretty tough.
So it's like if one of the small pieces contain the colors of the main theme, it would just expand to like the main object itself. So for that one, it would be the block with blue and green, and then it would just expand to that one single one.
I don't think that's the answer for this one. Does anyone else want to try?
The one with the least number of pixels.
The least
it becomes the full picture in itself.
Oh, interesting. That's not true of the second example. Like, this is a really tough one. Don't feel bad about not getting it. Anyone else want to take a crack at it? And then I'll just show what it is. All right, I'm gonna leave. Okay, here's what's happening, and this is a mean one. So take the largest kind of agglomeration of objects, right? So if we look at, can you see my pointer?
Yes.
Okay, great. So you see this very large sort of object. We know, or we think we know, that because of symmetry, this should be extended out beyond the beyond like the boundary of what we're looking at, right? So this is a little bit of like object persistence. Whatever that is, we need to take a look between the two objects and then say, oh, okay, this object is a smaller version of this object that we only partially see. Does that make sense? Or take a look at this one, right? So this one should be extended out very slightly in these different directions, and that matches the yellow as well. And then by the same kind of token, you have a very large 5 that is barely visible at all, which I think that this one is especially mean, right? So this, the the test here would extend out the little cross to have a base that would be light blue, and then you would match it to this, and you go, okay, and then you select that item. So that's a really tough problem, I think.
How many of them look like this?
So there was a little bit of bias. So actually, so kind of like important point here. None of them look exactly like this. So that's what makes this a really challenging problem, is the same sort of logic does not apply to any of the tests. Or actually, there are a few ones that are kind of like overlapping, but you'll never see another one of these. And mind you, this is a training example, right? So if you have a way of solving this example, you are not going to see it in the test set, right? But there will be problems that are maybe kind of like this. But in terms of difficulty, this was one of the toughest ones that I found. But there are other ones that are about as tough as this one. And there are some that I don't even know the answer to. Does that answer the question?
Yep.
So again...
Oh, are these procedurally generated?
No. They were all done by Francois Chollet himself, as far as I know. And we'll talk about this a little bit more, what he really wants is to get at this sort of skill acquisition efficiency, right? And what he doesn't want is for all of these intelligent systems, all these AIs, to just work on trying to crack the generation algorithm by like the procedural generator, right? So there's a little bit of a problem with this. If it's a human who has to design each one of these, it's not super scalable, but many of the tasks are still secret, so it's still pretty useful. All right, so we have finally got to the definition of intelligence, which I assure you is absolutely objectively correct, and no one can possibly find any fault in this. The intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. What does that mean? crap. Spent all this time trying to tell you, oh, here comes the definition of intelligence. And honestly, when I first read it, I was like, I do not understand what he means. So he helpfully gives you a mathematical formula to explain. And I'm sure everyone just looks at that formula and goes, yes, that is what intelligence is. So I'm going to very quickly try to explain what is going on in this equation. What is really great about this this definition of intelligence is because you can formulate it as as an equation. That means you can optimize it, which is exactly what we want to do. So this is actionable in his terminology. So just on the left here, we have I. That means intelligence, right? And then it says you got this theta t, which is sufficient skill to solve like a task, right? And then you have for a given intelligent system and for the scope of tasks. So of all the possible tasks, this is the intelligence of whatever system, right? And then I want to look at over here, I'm going to go kind of right to left to look at this other side, right? We have GD, which is generalization difficulty. So if we go back over here, I think that if you were given 20 examples of what is going on in this case, right, you would probably get it a lot faster, right? But you only have 4 examples, so it's tough, right?
So I have a question.
Yeah.
Do you predict the colors too of each picture?
Do you predict what? Oh, the colors? Yes.
Of the picture.
You have to. So in this, it's a very rough kind of task, right? Because if you get any of the colors wrong or the size of the output wrong or like any pixel off, that counts as a failure, right? So it's pretty mean. But yep.
There's also a problem with this formulation of intelligence.
Mm-hmm.
I think something like that. Maybe median or mean average precision, like maybe because you may not do well in all the taxes. So you're encouraging average thinking, so which is actually limiting in itself. So people are good in just a subset of goals and then do badly in some other goals. So,
yeah. So
he's assuming that it's like average thinking, which is also not good.
So not average thinking so much as sufficient thinking. So it's sufficient. You have enough intelligence to sufficiently solve each one of these tasks, right? But that doesn't mean you get to it in a particularly fast way, right? It's just that like you eventually get the solution. Like it might take you several days to do it, but you get to it, right? And this equation, there's one that is very, very similar to it that is the optimal case. So it's like the optimal intelligence. So yeah, it is slightly different, but I agree on the sort of distance metric here. In fact, you'll see that the second place solution, they end up just using something similar to like the mean average precision as like their internal metric they're trying to optimize for. So just going to quickly get back to this big honking equation, generalization difficulty, and we're just going to kind of think about it. So if generalization difficulty is high, right, if you manage to solve that given task that has a high generalization difficulty, that's evidence that your intelligence is also high, right? And then look at the denominator here. You have P plus E. P is priors. So if you just encode, this is how you solve equation task 55, right? That's not really intelligence, right? Like you just like, it's like, oh, well, that's just like a sorting algorithm or something like that, right? So you want to not have all of that information there. So you want a low amount of relevant priors is what he says. And he also says E is experience, right? So if you have more experience, if you spent more time training and you've had more examples, right, we should penalize you in some way because we care about the efficiency of information acquisition, not necessarily how smart you are overall, right? So it'd be kind of like, well, I trained on a ton of external data with a lot of problems that are like this, and now I'm coming back and I'm trying to answer all the art questions. Cholet would say, oh, like your machine is not as smart, right? So as experience goes up, the intelligence goes down. And the same for priors go up, intelligence goes down. Lastly, I want to talk about this kind of sum over C, and C is curriculum. So he's really interested not only in like the training of these algorithms, but also like the order in which you train things. So he is talking about a curriculum, which is, you know, just the training set plus the order in which you train things. And he says, okay, over all like possible curricula, how well did you do? Obviously, this is the kind of equation that looks very complicated and seems to like say quite a bit, but it's one that you can never really solve. It's extremely difficult to solve. Just thinking about like, well, how do you measure average performance over all possible curricula? Last little bit here. This is where things get a little bit subjective. This little omega here, that is someone's opinion about how hard the task is in general, right? So not only the generalization difficulty where we would increase the amount of examples here, but also just like overall, like how many steps do you think it would take to solve this, right? And that is subjective. But this gives us at least something we can optimize for, which is great. What does that actually tell us? Essentially, it just makes intelligence an optimization problem, and we can compare humans to AIs. Now we are actually getting to the competition, and Cholet, like obviously this is a very difficult problem, and a lot of people didn't even know where to start with this because it's so different from everything else that we've seen in Kaggle. So he drew Cholet drew a helpful diagram, and he says we need to be thinking about machine learning problems like this instead of how we normally think. So you have an intelligent system, and I'm just going to use the example of a neural network here. The intelligent system is the algorithm that you use and the way that you optimize, and it's kind of like everything that you do to program and set the hyperparameters, et cetera, right? What happens is it makes a skill program. So when you are training a neural network, right, the output of this training process is just like a big array of a bunch of numbers, right? So that's what Cholet counts as a skill program. And then what you do to see how good the skill program is you ask a task to give it a situation. So if we're trying to classify cats and dogs, you say, hey, give me like a random image of either a cat or a dog. And then you take a look at it. The skill program says, oh, this is a dog. It turns out that it's a cat. Then the intelligent system is given some feedback that says, hey, your skill program, like your random set of numbers, was wrong about this. So you need to change something about the skill program in order to make it better. And that just happens thousands and thousands and millions of times. And then you get a working neural network. And then when you get into the evaluation phase, you just remove the intelligent system, the training regime, and all you're left with is the skill program, which is just this array of numbers. So this is a little bit different than how you would normally think about an AI system, but it's important for later. Does this make sense?
Yeah, it makes sense. It looks like the 1960s SPAT system kind of stuff. Yeah, it's similar to those. Yeah.
Okay.
It makes sense.
Okay, cool. Right. Let's actually get to this test description. So we have 400 training tasks. We have 400 like public evaluation tasks, right? So those are available to you, so they don't have answers. But because we are intelligent systems, we can solve these answers. And in fact, a lot of it seemed like the winning solutions ended up looking at those public evaluations and just solving it themselves. And then you have 200 completely private. They're still locked away. We don't know what they were. It's a test, test tasks, right? There can be up to 10 unique symbols or colors in each task. Most of them will not have that many. The size of the output and the input can be 1 by 1 up to 30 by 30. And they don't necessarily have to agree. Like if we go back here, you'll notice that the input is much larger than the output in every case. There are usually 3 examples with a maximum of 5 examples per task. A typical human can solve most ARC problems with no previous training. So we went through 4 of them, and it's pretty indicative of how hard these are. Most of them are relatively easy, but some of them are quite difficult. then Cholet kind of makes an aside, well, not an aside, but he just says in a single sentence, at least one of 3 high IQ humans were able to solve each task. And I think this is a little bit unfair to machines, right? If we're saying, oh, these priors all humans have, and he's saying, oh, well, at least one of 3 very smart people were able to solve the problem. It seems like this data set is just very, very difficult. What I kind of want is ARC for babies, that they can just like point at, oh yeah, I want the purple dot or whatever. But the intelligence system gets 3 guesses per task, right?
Matt, I have a very naive question.
Yes.
So
That's
right
my
at the
question.
introduction, we were talking about the black swans, unknown unknowns.
Yeah.
But the whole test data seems to be very methodic and has a bit of pattern and and leading aspects to it, right? So that kind of conflicts with the whole intention of a system that doesn't recognize patterns, because we are trying to build a system that understands unknown unknowns, right? So how is the connection happening here? I mean, just being.
Yeah, this you said it was a naive question. That's a really good question. So I guess what I would say is the basic building blocks of all of the problems are the same, right? Find symmetry, things like find the largest object, complete this sequence, right? All of those will be present, at least to our knowledge, in the private evaluation set, right? The order in which you have to apply those functions will not be in the training set. So, and this is actually like kind of rough to think about, right? Like, if you train, and actually this, I had an idea of like, oh yeah, this is how I would do it. And I realized it's totally bogus, won't work. So you would think that if you look at all the training data, right? Let's say the most common like type of operation you have to do is a find symmetry operation, right? That may not be the case in the private data set. We just don't know. There will definitely be some problems that involve finding symmetry, but like there's no guarantee that it is actually there.
That makes so much sense. Yeah, that makes so much sense. Yeah.
But it just takes a little while to kind of wrap your brain around like what is actually being asked of the system. All right. No crystallized knowledge, no NLP or object recognition. These challenges weren't programmatically made. Okay, how should we solve this? Cholet kind of recommends we do something called program synthesis, which is something that I was only vaguely aware of before looking into this challenge. And I think it is a really cool idea. So the idea is you make a bunch of like very basic functions, sort of like add, divide, actually divide might even be too big, but add, find symmetry, et cetera, using domain-specific language, so like a subset of Python or whatever language, right? And then your job, or the AI's job, the intelligence system's job, is to figure out a way of composing these very primitive operations together in order to create the solution that we want, right? So this is pretty different from how we typically think about machine learning, which is usually like build a big array of numbers and multiply them all together until you get a cat, right? This requires a little bit more finesse, right? Because the quality of your domain-specific language and like the composability of it is a huge factor in how well you do here. Just a few weaknesses before we actually get into the competition, and it is probably like 7:45, I'd guess. Yeah, 7:54. So I'm going to go over. Well, we might actually go over before actually seeing the competition. ARC could solve so an ARC solver could have human-like intelligence or not, right? So that's the AI effect, right? Maybe there is some solution to this that is just bone stupid, and we're no closer to AGI, but at least we tried. Generalization difficulty is not quantified. I see this is actually an old slide, so it needed one more commit. Test validity is not established, so we don't know if an ARC solver is actually going to be useful in real life. Dataset diversity is limited, right? So we're looking at the same like pixel graph over and over again. Like there may be something qualitatively different about trying to deal with, say, sound, some sort of sound problem. that an ARC solver just won't be able to get to. Evaluation is very close-ended, so you get a 0 or 1 depending on if you get the result back. And this is mostly, I think, so that you can't go fishing for what the problems are, right? So there's no kind of fractional results. It's either you get it or you're not, or you don't. Priors may not be well captured in ARC. One prior that I thought would be really good to have, this was mentioned in the actual Kaggle forum, is, oh, hey, we know that the black pixel means like background, but nowhere in the priors that you enumerated do you say black usually means background and gray usually means wall, right? So that might be a prior that you would want to encode for. Okay, well, what do you win? Well, you would probably become one of the world's most famous computer scientists, but you also win $20,000. That's good. Right. 20% of tasks, surely I would say would be a really great start for ARC. And the winner, 20.6%. So we have surpassed expectations. Still a long ways to go. And when you look at the guy's solution here, this is the winner solution. He essentially says, well, I knew how to code C++ really well, and most data scientists don't. So I just made my DSL as fast as possible, and I tried as many combinations as I could. I just totally brute forced this thing. And yeah, it worked. So it worked 20% of the time. So kind of intellectually that feels like a disappointing result, but it also kind of shows us what the baseline is, right? Oh, I should say that each ARC solver, you submit the code, and it's given 9 hours to run to solve all of these problems, right? And at the end of 9 hours, it's like test time is up, and then you find out how many it was able to solve. So, C++ really fast. That's good. Another kind of interesting approach here which actually was quite close, and it was done in Python. Was essentially to use this evolutionary type strategy where you would you'd have these pairs, right? And then you would apply random functions to the input and see if you got closer to the output through this kind of pixel-wise distance, right? And you would only keep the top 3 of these random these random combinations of these different functions. So there's a little bit of evolution going on here. And that got them to 19.7. But one of the things that I found really interesting was for 6 weeks, they were not getting above 2%. And I think actually 2% was enough to get you bronze, which is like the 50% mark, right? So these are not even indicative of what the average results. I think the average result was like 3% by the end. And that is it, right? So I'm going to leave you with a final question here. Actually, I'm glad Kiri is here because we had a little talk about this, about when do you think an algorithm will outperform humans in the ARC challenge? And actually, I would love to ask, do you think it will matter? Is there stuff going on in the chat? I can't actually see chat right now.
Too good of a question.
Yeah, it's a thinker. Kira, I don't want to put you on the spot, but do you want to say what your guess was?
I think this competition the score will get the algorithm will get 80% of the stuff right within 3 years.
Yeah.
But follow up, do you think it'll matter?
Yeah, I think where things like text generation fall apart right now is that it's missing the ability to put together a coherent story, and I think that this competition actually exposes the inability of algorithms to sort of to make a story to reason. Mm-hmm. But I think now that there's this problem posed, that people will be working on it. I don't know. I already have ideas about how I would do this. There's a talk by Yacho Bengio about, he calls it, I think, second order.
Was that the NeurIPS keynote?
Yeah.
Yeah, it's a good one. It's definitely worth looking up.
Yeah, and I think now that people think it's an important problem, then there'll be lots of people trying to optimize for it. I think actually with this competition, they weren't necessarily expecting there to be a lot of progress on the problem, but I think what he really did was he wanted to find out how good his benchmark was. And I think my suspicion is that they're going to rerun the competition again in a year, and they're probably, I think they're going to change the problems up a bit. My guess is that the way the competition was structured, there's an input and you have to predict an output. I think that you can generalize that to an arbitrary number of inputs, of which you may have to predict the third element, or you might have to predict the fifth element. But you have a couple of examples where you have, maybe the first example, you have the first four elements and you have to predict the fifth element. So I think there's ways to make the test set to generalize it. And I think they just wanted to find out how difficult the problem was and how much headway people could make with just grinding away with efficient C++.
Yeah. Yeah, I think that is all like very smart. For me personally, I think this is something that we will solve the first arc in probably 5 years. And then by the time we get there, though, it's going to be like, okay, now what? Because I think what's going to happen is someone is going to figure out like a really nice, efficient tree search algorithm, and it's going to be boring, but it's going to work really well. And then they're going to go, okay, yeah, but now the next thing.
I don't think this is a search algorithm. I think that whatever human beings are doing with their brains is the same in hardware that we are running like cat detection on is also being used to reason. And I think probably the secret to this problem is attention. And I think Yosho Benyo also said this in his keynote presentation. But I don't think, I think whatever we're doing with our brains, that it's doing cat detection, that should also happen when you're doing reasoning. And I think, if we're going in the right direction of the right algorithm, I think that we'll start to see progress on this problem.
Cool.
I guess ARC solvers don't get to train on the secondary task of cat detection, right? So,
not yet.
like the insistence that we learn to solve ARC problems by studying ARC problems, like that is not anywhere close to what the human is doing. I think that's significant.
The thing that I would imagine though is like we'll start to see deep learning algorithms that like their goal is to compress down situations that are like really rich and unstructured. So like images, compress them down into ARC-like problems. So you can imagine like a semantic segmentation that just encodes these sort of pixels that the ARC solver tries to get.
I think it would be a useful tool.
Okay. Can I just ask you to
retraining your ARC competition solver on cat pictures as well?
Yeah. Sorry, who was also talking? I'm just gonna.
I was just wondering if you could just go back to one of the earlier statements you made right off the bat, and it would. I don't have the same level of understanding of AI that you do, but could you explain why? I think you made the statement: deep learning obviously can't address this problem, and I wasn't really sure what the basis for that statement was.
Yes, I really should have explained that. Thank you for pointing that out. When we look at, say, this right here, one of the things that deep learning, so first of all, without even getting into the math of it at all, deep learning tends to be a very data-hungry type algorithm, right? So one of the things that people really like about deep learning is you can give it 1 billion data points and it will still keep on improving. In some cases, that's not true for all cases, but it tends to have like a higher carrying capacity for data versus a more traditional, let's say like a decision tree type algorithm. So we don't have a lot of data here, so that's not good for the deep learning algorithm.
You don't have a lot of data because of the nature of the competition, or because of something intrinsic?
Because of the nature of the competition.
Okay.
The other thing that's happening, and this is also in the nature of the competition, so like it's almost, well, it's not almost as if, it is that Cholet was trying to show kind of the rest of the machine learning community, like, hey, neural networks are not everything. And there's a whole field that is underexplored. And he essentially tried to construct a data set that would show that neural networks would not be able to do this. So the other part right here is the feedback that you get in the ARC data set is not conducive to deep learning. So deep learning requires these things called gradients, so like the derivatives of error, and that does not exist here. You get 0 or you get 1. There's no, oh, but you were close. And that is basically, I wouldn't say it's impossible for a deep learning algorithm to adapt to, but like extremely, extremely difficult.
But that was due to the definition of the error, wasn't it?
Yes. Yeah, so there is nothing intrinsic about deep learning that it cannot learn to solve these problems, but it will likely require many more examples. And in this particular case, because there's no gradients, it's just not going to work.
Okay, so it's really just asking the system to learn more quickly than deep learning could with far fewer data examples.
Yeah. Because it's looking at the efficiency of intelligence, right? The efficiency of the of skill acquisition over the overall skill. Right? Like overall skill, the neural network is going to win, but if it requires 10 million years to get there, that isn't super helpful for us.
Did he assess using kind of a gradient, like if you adjusted the error definition and then using a gradient algorithm? Has that been looked at, or is that in this case? Yeah.
Some people did test that out. It seemed like none of them really got very far with it. Like the second place solution uses a gradient free method, which is this evolutionary method. But others tried, so there is some research into neural program synthesis. So it's actually trying to make GPT-2, which is a very large neural network, supposedly can fill in some functions for you. I believe there's a plugin called Tab9, which uses a big GPT-2 model to predict what you want to write a function. It tries to write the function for you as you're typing it. So like a very smart autocomplete. So there is some research on that. It's just like it's very data hungry. It's trained on like the full GitHub corpus, or full public GitHub corpus, I guess.
Thank you. Interesting presentation. Thanks.
Thank you. Great, good question. Anything else? I guess we're probably over. So if people want to stay around though and ask questions and kind of see if we can do better than these people, love to stick around.
Okay, I'll take that cue as to put the punctuation on the end, but then we'll just continue the after party as appropriate. So thank you, Matt, for a wonderful presentation. That was great. I am going to give you some applause at a count of 7, and anyone else who unmutes themselves and applauses at the same time, then you will get a round. It will go 1, 2, 3, 4, 5, 6, 7. Yay! Yeah, that sounded like a few applause. That was good.
Thanks, everyone.
And we'll plug again. Do please come 2 weeks from now when we have the winner of a competition presenting. That should be amazing. And thanks again, Matt. This has been really thoughtful. I'd like to have more, so I'm just going to shut up and hope that somebody asks another excellent question. I mean, I do feel, I do want to go back to what I was saying, that I don't think it's fair to expect a system to learn from only ARC examples to solve ARC examples like a human does.
Yeah. What would you add to make it fair?
So I had a little look at some of the notebooks from this competition, and I noticed so there was one interesting example that was trying to explore cellular autonomous the idea that you're somehow inputting some kind of spatial component into sort of trying to solve it. I mean, is this what you'd be thinking in terms of these kind of human priors? The idea that you're somehow within, with a neural network or something, it's hard because there's no real kind of structure to say that these two things here are kind of related or not. But then what is the sort of fundamental model that it should look like that would incorporate those kinds of priors in that kind of quite generalizable way, in the sense that the priors typically are, things that are defined on the real line, right?
Yeah.
Well, even it's the domain that we can define here.
So this is a completely uneducated guess, is when I was looking at this and trying to apply neural networks, right? Because that's what that's what I want to do, right? I was thinking about like capsule nets and the idea of, neurons sort of firing together in a group-wise fashion instead of like individually. And I thought, oh, that might be like an interesting thing to do. But I fundamentally think that like any neural network is going to be too slow unless we get like really awesome convergence, like really awesome like optimizers that we just don't have yet, because 3 examples just isn't enough. Although, like some people were doing cool augmentations where they were flipping things diagonally and stuff like that, trying to get more examples. And whether or not that makes sense, it's kind of hard to tell, right? Because they're like, if we look at this one, I guess like I was going to say, maybe there's some sort of like implication of gravity here, and it's like something kind of growing up. But you could flip this so that it becomes horizontal, and it's just as valid, I think. Although actually that would totally fail this if you did the flip here, and the rule is go up until you hit a gray block and then go right. Oh, by the way, do you guys just want to like, as we're talking, like I can just share like random ones, and you guys can just think about them as we talk.
I just wanted to.
That'd be fun.
Yeah, that'd be great. Do that.
I want to go back to what something Curie was saying, though. She was saying that the cat recognition problem is a good one, but I was wondering the human brain doesn't work like that, though, because we don't need to have a physically manifested thing, and we can still reason and imagine those things in our head and create solutions for problems.
Right.
Whereas with any kind of systems right now, they don't have that kind of reasoning. Because I think at the end of the day is how abstract reasoning can a computer have is what this problem is trying to solve, right?
Mm-hmm. And Curie, sounds like you were about to say something.
With what you were saying about augmentation, when you do something like rotate, the example you were just showing, you're adding more items to the training set for that task. You're actually just generating a completely new task.
Yeah. That's what I thought too. I think that's kind of like a classic Kaggle thing. Is like, well, the results seem better when I did that, when I added this augmentation, so I'm keeping it, even if it doesn't even make logical sense, right? So yeah, I don't think it is super useful. I kept on wanting to be like, yeah, but what if we could generate more examples? But
did anyone
more examples? You would have to be pretty smart. What's up?
Like, did anyone reverse engineer Cholet? After studying these examples, I think I could write an algorithm that generates them.
I think really that's the goal too. It's kind of the backwards goal. If you can generate more tasks, then you've solved the problem. How do you solve the tasks?
Yeah, but my goal isn't to make AGI. My goal is to win Kaggle competition.
Yeah. There was some guy very early on was like, can I just try probing the leaderboard over and over again? And Cholet just came in and was like, yeah, sure, do whatever you can. And I checked to see where that guy landed, and it was I think it was about 30th place, so not terrible, but probing the leaderboard isn't going to get you everywhere on this, because you got to remember the tasks in that private data set do not exist in the training set.
So I was looking through this cellular automata. Yeah. So I think what would be the reason why it failed? Is it because of the color constraint if we relax the constraint of colors, for instance, and begin to evolve shapes, and if we have a way of putting our priors of the kind of shapes we, from what I saw, a cellular automata is the more promising way of doing this automated.
I think for like the previous task, it looks like it could do that well, where we're sort of trying to grow those shapes and sort of avoid the boundaries. Like you could create a cellular automata that would do that in a meaningful way. But because often you're sort of assuming that there's sort of only, you can define your own neighborhood structure, right? But typically it'd be the sort of nearest neighbor kind of thing where your rules are based upon what's around you. Whereas like, so this example is great because it's like, well, there's a shape that you've got to somehow, maybe you've got to flip it, and then you've also got to sort of move it to another part of the board. Mm-hmm. And a cellular automata, unless you're sort of defining it, it needs some kind of memory structure of the whole board. It needs to know that shape, what that shape representation is, and it needs to know, not to stretch or transform this, just keep it the same shape and possibly flip it. Mm-hmm. And I think, I don't know, when I was having a look through some of those ideas, it was more this kind of, you're trying to create some local rules within an area, which I think would probably be good for some tasks, but like this task, I imagine would just fail horribly at.
Mm-hmm. Yeah.
Thanks a lot.
It wasn't clear to me whether cellular automata would actually, whether there was a way to show that was a way to solve all the problems. Like, is there a way for every problem in the training set that you could solve those problems with a cellular automata? That wasn't actually clear to me. And I think the cellular automata might actually be I saw another paper where somebody was showing that you could express cellular automata operations as convolutions. And so my guess is that whatever cellular automata are doing and whatever convolutions are doing are probably specific cases of a more general way to formulate the problem.
Interesting. Yeah, I really don't know enough about cellular automata to add anything to this conversation, but it's really interesting.
If you guys want to spend more time on this competition and you want to read a really great kernel, the cellular automata kernel is really well written and interesting. And even if it's not something that ends up getting used, I think it's interesting reading.
Can you post it in the chat?
Let me try to get that.
Don't mind me. I'm just gonna kind of solve them as I see them. That was one of the things. It's like some of them, like that previous one I had seen before, and like I'm pretty sure I had it solved, but I didn't want to go through the effort of actually like doing it. So I might skip a few.
Hey Matt, what tool are you using to bring up these examples?
Oh, yeah, I should have mentioned this before. So François Surlet has released a little viewer for this. If you just go on to GitHub and you search for, by the way, I'm LSTM Emery at GitHub if you want access to my presentation, etc. But yeah, FSHLA/ARC, it's all there, which is kind of nice. Okay. And you just click on testing interface and that gets you there. So
I think I mentioned in the reading group that I have a very young person I want to try these on.
Yeah, that would be really great. I really want to see like an ARC for babies. Oh, what the heck? Oh yeah. So like there's some stuff so I cut out a lot of stuff. And I kind of wanted to share a little bit with you guys if you're interested. So I completely elided how things like generalization difficulty and like priors and experience were actually calculated because it's very theoretical, but I think it's kind of neat. So the way that you would do that, and this is something that you would never do in practice, is if you're trying to figure out how difficult something is, you want to write a Turing machine, and you look at the shortest possible Turing machine that you could write to solve the problem, and that's how difficult it is. So this is taking from algorithmic information theory. And if you have not like played around with Turing machines before, I would highly recommend you do, because they're crazy. Like it's awesome that someone actually was able to figure this stuff out. Because like I definitely not in a million years would have figured it out. Go play around with Turing machines if you haven't. But the way that all that stuff would be measured is like how short of a sequence of ones and zeros could you make to encode the idea behind each of these tasks.
Is that actually a solvable problem?
No.
It sounds like
really.
it's something NP hard to get the shortest. How useful is it as a concept?
Not very useful, but it turns out that it is related. I guess the upper bounds of what's called algorithmic, or this, what he's calling generalization difficulty. The upper bound can be defined by how compressible a given program is, right? So if you take the binary of a program and you can compress it a ton, it's actually like not as hard as it looks. It just like, looking at the problem itself.
So I think that's from like a Kolmogorov complexity or minimum description length.
Yeah.
Okay, I see.
Yeah. So Kenneth said, it's the Kolmogorov. Is it Kolmogorov entropy, or I can't remember what the measure is? Kolmogorov complexity. Yeah, that's like what he ends up using, and it's kind of like a notoriously impossible thing to actually compute, and you just estimate it. That's all I have to say about that particular topic. I just found it really interesting. Spent a bunch of time looking at that.
Yeah, I used to see those in theoretical machine learning. I don't think people are implementing it in real life.
No,
it's one of those conceptual stuff.
Yeah.
in a space of its own.
It's like solve the Schrodinger equation. No one actually does it, but it's there if you need it, I guess.
Yeah.
I like to think about intelligence as being a compression algorithm, and the competition, like what you want is an algorithm that can find some transformations that allow you to efficiently represent the output image in a very compressed way.
Yeah.
And that's basically what you're doing. You're finding, what transformations do I apply to the inputs? And then you don't have to store them.
So the one of the people that I took from in terms of their definitions of intelligence, Legg and Hutter, Hutter has a specific challenge that is also trying to get at AGI. I think it's called the Hutter Prize. But essentially what it's trying to do is how much can you compress down the Wikipedia text and still like be able to work with it, right? Because he is very much of the idea that if you can compress it down, like you have better abstractions for what you're going to need for intelligence, which I think is actually pretty neat. And I think that's where Hutter and Cholet disagree for some obscure reason that I don't understand.
Did they disagree about that somewhere publicly in writing?
I don't know. I just know that there were people complaining that Cholet just stole all of this from Hutter, but he won't recognize Hutter even though he was cited a million times in the paper. So it was dumb Twitter drama that I've completely forgotten about, except for like in this case. But yeah, I don't know. Like, it was probably Twitter. Anything else? Like a new one.
Just want to say, Matt, this was amazing. Like so many really interesting ideas to think about, and like a really cool way that you walked us through it. So,
thanks. This was a really fun one to do. To be honest, like I've done quite a few of these presentations, but this one, like it really felt like, oh man, this does feel cutting edge. Like there's so many things to think about here, and like I went off in a million different directions and kind of like got to play around with a lot of the stuff. So. This is a kind of an advertisement, I guess, for doing one of these competition talks, because you end up learning so much, and for the most part, it was like really fun. And so for this particular one, if people want to know more, I would really recommend that you actually read the paper on this. It's called On the Measure of Intelligence. So a plug for my my GitHub. I have a bibliography with all the sources that I used. So everywhere where I quote people and a few other interesting sort of links. So you can just go through there if you want to peruse. But On the Measure of Intelligence is really an interesting paper. It's not like any other computer science paper I've ever read. It's a long one, but really, really interesting.
It's a long one, but it's really nicely written.
That too.
It's very clear.
So cool to be alive during this time and to be watching these things evolve. This competition is going to be held every year, I think, by the sounds of it, and just like being there for the first one, seeing how well it's doing, and then it would be great if you would present again next year, but no pressure. Somebody else will cover it. It was just so cool to be able to kind of watch as these things evolve. And,
Yeah, so in Kiri, you can kind of attest to this too. When I first kind of agreed to do it, like I was very much coming from the angle of oh man, like we are so far away, and like there's so much hype going on. And then the more I read and the more I dug into it, it was just like, oh, this is such a difficult problem. And the fact that people are even like attempting to tackle it right now is actually really impressive.
But the same thing happened in computer vision because
yeah, exactly. Yeah, sorry.
Would have said in 3 years' time we're going to be like, having an algorithm that can take a picture and then turn it into a Van Gogh.
Right.
That just seemed like science fiction, and then 3 years later it was reality. So I think this technology is going to go faster than people think, and I think that now that researchers are aware of this problem and there's some reward for going after it because it's in it's Google and it's F. I think that it's got some exposure and that there will be some attention on it. So.
Yeah.
So I bet, Matt, that at 3 years that this problem would have a score of 80% correct rather than 20%.
Yeah, I'm not sure if I said my actual number or not, but I'm thinking it's 5 years.
We're going to mark our calendars for 3 years. We'll have a reunion meeting.
Yeah.
And then see what the progress has been.
What is going on in this one, by the way? I guess it's... Oh, what?
It's like...
How does it fill in the colors? Doesn't have to be...
It's the size of the square thing superimposed over the blue shape.
That's the...
And when there's no colored thing, then the light blue shape shows through.
But only in the center, right? So
yeah, if there's an overlap in the center, then it gets colored in by the side that it's closest to.
Yeah.
Okay. Yeah. Oh man.
But we don't know what happens in the very center because there's no examples of it overlapping in the center. So what color does it get there?
It probably just stays light blue based off of this one.
We don't have to worry about it because the test set item doesn't have that problem either.
I'm going to try to solve this one and see if we get it, but keep on talking while I do this.
Actually, I'm reading this wrong.
Actually, one of the interesting things about the problems was that sometimes they had more than enough examples, like it was overdetermined. You didn't examples that were in the training set in order to figure out what the rule was.
This is interesting as the size varies as well. So, and the size of the test is different to any of the examples, isn't it?
It looks like that.
Mm-hmm.
That's another thing. Like even just thinking about like how do you get the size right? Like when I was thinking about like how would you actually solve this? Like, oh man, that's really tough. All right, so then I'm just gonna paint in the whole thing, and then we'll color in as we go.
Because you see, like there's kind of sub problems here that if you solved a sub problem, you'd like to give that some value. Like getting all the colors in the right on the boundary correct. I mean, that's at least something, right?
Yeah, I agree. So one of the things, like psychometrically, that I wish that they did include as well would be because there's no actual measure of like generalization difficulty or like any kind of difficulty in these, like getting this one wrong, I would feel a lot like better about than getting the very basic one of the thing drops down one.
Yeah.
Right. So like there really should be a differential score for this. And yeah, you're right. Like you should be able to solve a subproblem. Like when we score, let's say like a grade 5 student in division, right? What we'll do is we'll look at, how far did you get, right? Like how many, significant digits do you get correct? But also like, are you doing it in the proper way or whatever? Are you showing your work essentially?
I mean, for example, in this one here, right, because of how you're sort of filling it in, you could have the situation where actually the rule is that the filling in colors have to be a connected set. And so say in the green and the bottom, it could either be it's just the left one that's filled in, or it's both. But actually, any of the sort of examples doesn't completely determine what that rule is.
I took it to be like this.
Yeah.
I'm gonna try it and get it wrong, and then we'll see.
Yeah.
And is it like?
I
think if the middle one is touching the border, it gets painted over in that color.
Wrong.
Oh, you missed the yellow.
No, yeah, you missed a blue one as well. Wow.
So, okay, I'm going to repaint this.
I think we all have a slightly different idea of the solution, which is kind of to Mike's point.
Yeah.
And I think everybody's solution is actually just as valid as each other's. So this is actually a really great example to go through. I wish we could all load up this exact problem.
Yeah. Well, you can if you want to grab that. Oh, crap.
Oh, no. Go back. Can you go back, please?
No, it's JavaScript too. That was not intentional. I did not know it would do that. I'm sorry, guys.
That's okay.
Yeah.
I think we got to a good point of that one anyways.
Everyone's homework for the next time is to find that puzzle again.
It was like 267
I can just assume that I was right.
Yeah.
Well, I'll assume we're right.
That was me like solving the problems for the talk. It was like, yeah, I'm pretty sure I got this. Go to the next one. Oh yeah, this one is just kind of sequence completion, but also kind of a nice one.
I was going to add that I didn't see anybody in the competition who came up with a good way to like figure out what are going to be your top 3 guesses. But you do have 3 guesses to how that you get to plug in and see whether any of them are right.
Yeah, I'm trying to remember what the first place guy was like. The one or the second place ones was like it was the closest pixel wise, and then also like the simplest routine that got you something. I'm trying to remember what the last case was, but yeah, it did seem kind of random, and like maybe that's a way to do a little bit of leaderboard fishing and stuff like that, is to just switch up what because like your first choice is probably going to be like, this is the one I think most likely is the answer, and then your second and third maybe like safety picks, right? But yeah, no, I didn't see anything that kind of blew my mind. Oh yeah. Yeah, so this one is just like it would be like another compression thing, but you just don't care about the geometry of it. It's just like the topology of it, right? 1, 2, 3, 4, 5. No. Right. I'm probably gonna head out in a little bit because I'm tired. It's took a bit to do. But any other kind of questions, like things for discussion? Oh, I was way off on this. 9. Okay.
Thanks, Matt. I'm going to head out too. It was a pleasure to connect with all of you. It's been so long.
Yeah, it's always good to see a familiar face, hear a familiar voice.
Have a good long weekend. I'm sorry. Have a good weekend, all.
Yeah.
Bye.
Thanks, Matt.
Yeah, thanks, Matt. That was really great.
Yeah. Thanks, Matt. Bye.